If you take a smooth function and you multiply a test function, it's again a test function. If you compose a test function within a affine transformation onto Rn, it's again a test function. And if you take the convolution of two test functions, it's again a test function. So that's pretty neat. He then defines convergence of test functions. So you write that down. I really think if you look at that bump function, what you have essentially is something of the form e to the 1 over x, let's say minus 1, and then times something else, right? And so if you think about the Maclaurin expansion for that, what is it? See, you're looking at the sum 1 plus 1 over x minus 1 plus 1 over x minus 1 squared, 2, right? Plus 1 over 6 times x minus 1 cubed plus da 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 times this other piece. Now the other piece is analytic at 1 because the other piece is based on the 1 over x plus 1 when you feed it to the laws of exponents. But if you look at, there's like a half also I'm neglecting at the moment, but that's why that example is like, this is the secret sauce behind the example, is like it's got an essential singularity at the edge. So the test function is not analytic, which is helpful because analytic functions have actually kind of special properties, and if you were to use analytic functions, it would limit your scope. I guess the test function, I suppose, that we were just looking at, it is analytic, not if you stay away from the endpoints. But okay, so definition, convergence of test functions. You have phi1, phi2, da 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 da, and phi in your test functions, all right? Then you have that phi n converges to, well, here's how he writes it. Phi n converges to phi if you need two things. A, you need that phi1, phi2, da 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 da, and phi vanish outside some bounded S, which is a subset of Rn. Okay, so there's got to be a common set on which, outside of which they all vanish, all right? And B, the alpha derivative of phi n must converge to the alpha derivative of phi uniformly on Rn for every multi-index alpha. So that's a lot. Now, his theorem 6.26, he points out that you have nice properties for these sequences, like the sum of two sequence, the limit is the sum of the limits. You have like a linearity of these kinds of sequential limits. If you have a smooth function times a sequence, it converges to the smooth functions times, like, let me just write it out. That one's easier just to write. F times phi n converges to f phi in this context. That's another thing. It also, the sequence plays nice within a affine transformation. And also, interestingly, the alpha-th derivative of the test of the sequence, all right, converges to the alpha-th derivative of the limit of the sequence. So you have some pretty nice properties for this concept of limit. That brings us to our definition of distribution. And this is really the heart of chapter 6 right here. By distribution, F on Rn, all right, we mean a continuous linear functional on the test functions of Rn, all right? In particular, you need A, F of A phi plus B psi is A F of phi plus B F of psi. So there you go, there's the linearity. And the continuous, what's meant by that is that if you look at the image of the sequence, it limits to the image of the limit in this way, in C. Whenever phi n goes to phi in the distributional sense. He says the space of all distributions is denoted D prime. All right. And, oh, and this is big. This is like the last time you'll see him write F of phi. It's like here on out, he uses the following notation. F of phi is equal to, all right, this is the notation he uses. Yeah, bracket F with phi. He says this is not an inner product, and there's no danger for confusion here because there's no inner product. But this is deliberate because while it is not an inner product, there are nevertheless similarities. And if you look back at the role the inner product played with Fourier analysis and the generalized Fourier coefficients, that's another place where the analogy at the start of the chapter is seen clearly. All right, so distributions generalize the concept of a function. Formally, a function on Rn is not a distribution because its domain is not D. However, every locally integrable function f on Rn can be identified with the distribution in the following way. So any locally integrable f on Rn has associated distribution. How? Here's how. F with phi, how does it work? Well, you integrate against this here locally integrable function. And that makes sense, right? Because you're dealing with test functions. Test functions are only non-vanishing on some bounded set. And so your locally integrable function times another usually zero function, that still is an integrable function. So that makes sense. You can do that. And definition, f is called, so f, if there exists such f for given big F, then the big F is called a regular distribution. Otherwise, it is called a singular distribution.
Did we define D prime?
D prime is the set of all distributions.
Oh, okay. So
It's not an operation, it's just a label. Yeah.
Yeah.
Okay, so really, really cool example coming up here. So what's an example of a distribution? You've actually already dealt, I mean, man, the step functions we were playing with earlier, they're practically already there. So this next example is what are called Heaviside function. Heaviside function is not a function. Well, is it? Maybe it is. Well, fine. So here's his example 6.2.9. Let omega be open in Rn. Now he says that you could just use a measurable set if you wanted. Then the functional defined by, here it is, f v equals to integral over omega of phi, all right? You remember what that meant, right? That meant that you multiply phi by the characteristic function and integrate, right? That's a distribution. In fact, it's a regular distribution. Why is this a regular distribution? I mean, it's easy enough to check that this is a distribution, right? Does it have, is it linear? Yeah, because the integral is linear. And it's going to satisfy that limiting property if we get into it. It's also a regular distribution because this is, by the definition of this stupid thing, the integral over Rn of the characteristic function of omega times phi. So therefore, it is a regular distribution. And in particular, if you look at omega equal to the open ray from 0 to infinity, Cartesian product with itself n-fold times, then this gives you the so-called Heaviside function, which is, I guess, actually a distribution, right? Oh, okay, so the Heaviside function, right? I think here what I would be tempted to write, and I don't think he writes this in this book. So that's a distribution. Now this is a regular distribution, which means it's the integral over Rn of some function. I would call that function the Heaviside function personally. So like this is actually integral over R, integral over R, you know, n-fold times, right? And then my usual notation is this: u of x1, u of x2, dot, 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 u of xn, phi of x. dx1, dx2, dxn. Here, I also call the unit step function, I'll use a t here. U of t is equal to 0 if t is less than 0, and it's 1 if t is greater than or equal to 0. The unit step function, so I would say the Heaviside function in Rn, you could say it's the product of, I mean, I don't know. I mean, this is I would say this is an example of a Heaviside function. Maybe this is technically the Heaviside function. I'm not versed in the literature of this stuff. You know, I don't know, but this is essentially playing the game of unit step functions, but kind of for like, I don't even have the name of it, but it's for the, it's one. This thing is 1 when where all of the coordinates are positive, right? And it's 0 anywhere else. So like in 3 dimensions, it's 1 in the first octant, and it's 0 in the other 7 of them. In the plane, this thing is 1 in quadrant 1, and it's 0 in quadrants 2, 3, and 4. All right. This is a good example of a regular distribution. A good example of a singular distribution is called the Dirac delta distribution. Now we're going to define it carefully. When I move, you move.
Yeah.
See here.
So I'm starting to see the start of like, you know, like why like manifold, like calculus on manifolds became so interesting, but the book doesn't really go into that, does it?
No, I think that that's a good question. Where is the calculus on manifolds? And
Because this like seems like right in that, like this seems like the start of that.
you know, this is an interesting question, Audric, because I know of books that do careful real analysis. I know of books that do careful functional analysis. What's a book which does careful manifold analysis, right? Because that's the merger of this discussion and another discussion altogether. I don't know right offhand.
Well, I just know from like my studies of calculus on manifolds back during my argument and stuff, like this literally like has like the motivation behind for where we started on calculus, manifolds and calculus.
Mm-hmm.
Manifolds and calculus.
Yeah, I think, I want to say some of this kind of careful background stuff is likely in, what's the name? I think it's a Lee Group book. It's Werner Lee Group. I'll send you an email later. Okay, so Dirac delta distribution.
You're good.
Okay. Dirac delta distribution. And here's how it's defined. So the notation is delta. What does it do to a test function, phi? You know what it does?
It's a 0.
it evaluates. It turns integration into evaluation. He says the linearity of delta is obvious to prove continuity. He gives an argument. Let's see here. Well, he says thus phi n of x goes to, fine, I guess I'll write it down. If we have phi n limits to phi in the test functions, that implies the phi n goes to phi uniformly on Rn, okay. And that implies that phi n of x goes to phi of x for all x in Rn. Therefore, it's a singular distribution. Well, he doesn't say therefore it's a singular. That is just the proof that it's a distribution. To see that it's a singular distribution is, I guess it's just a matter of, well, I don't know. You'd have to.
Definition, since you're evaluating at 0.
you'd have to prove that there does not exist a function f, right? I mean, in principle, you'd have to say, well, suppose this is equal to the integral over Rn, right? Of some function f times phi, right? It's clearly absurd because the value of the distribution depends only on the value of phi at 0. And you have different values at 0 for different test functions. You can't have one function you're integrating to achieve all these different. I mean, it's just, maybe you can make that more rigorous, but it is in fact a singular distribution. And let's see here. Oh, and he has his next example, and I don't have a, I'll just write it down because I think it's amusing. But you can also kind of level this up, and if you have, you can define a distribution f acting on phi by the alpha derivative of phi evaluated at 0. And that's for an arbitrary multi-index. He says the proof that that's the distribution is similar to the Dirac delta proof. All right. Okay, so let me go through his next calculation here. He says, when adopting definitions for distributions, we expect that new distributions agree with classical ones when applied to regular distributions. All right, so let me try to put what he's let me try to sell you what he's selling here. He starts out with f acting on phi is the integral of f phi. All right, great. And so if we have an operator a, well, so let's see here. We're looking for some operation on distributions, all right? So AF acting on phi, we expect to be equal to, we expect A to be kind of like something that generalizes from functions to distributions. So you kind of would expect the generalization to work in this sense. And he says if we can find a continuous operation, A star, which maps D into D such that this is equal to F A star acting on phi, then it would make sense to say that that's equal to F A star phi. And I think what he's saying is like this idea is used to define the derivative of a distribution.
A star is just the adjoint, right?
Yeah, well, no, I mean, he's a little more slippery than that. He just says if we can find a continuous operation A star which maps D into D, he didn't say it's the adjoint. It's not, I mean, it is not the adjoint. I'll just say that. It's like it, though. I mean, in terms of the notation, right? I mean, it looks like it. And so this brings us to the definition. If you have F a distribution, all right, then you can define partial F partial xk by is defined. It's a distribution, and it's defined by the following. So what you have is partial f partial xk on the test function phi is equal to minus the given distribution f acting on the corresponding derivative of the test function. And the reason for the minus is as you filter through this idea up here, with respect to the differentiation, we have integration by parts inducing the minus. And then more generally, if you...
Oh, is this like why we define it as such? Because it looks like an anti-conductivity?
Yeah, I think the reason we define it as such is because it mimics the adjoint,
Yeah.
really. And also,
Oh, no, I'm sorry.
it's a, okay. I mean, it's a circle of different things. It's that it's mimicking the adjoint. It's that it's the integration by parts formula and the connection with the distribution, the regular distribution with the underlying function. You know, it's a lot of things. And there's the definition for the alpha derivative of the distribution theorem, 6.2.13. If f is a distribution, then the alpha derivative of f is a distribution for any multi-index alpha. And the proof is given there. I'm not going to go through it. It's relatively simple. And at this point, I need to share with you a story from my youth. So I was let's see here. I think it was my third year undergraduate, if I remember right. I think it's my first year at NC State. My first semester, I was still electrical engineering, so I had taken like circuits, digital logic design, and I think I had modern physics. Differential equations, I had that my first semester. And so my second semester come along, and I got into, I already had credit for linear algebra from, my first semester I also took, if I remember right, I think I also took math, the analog of Math 200 here, Foundations of Math. Did I do that? That can't be right. I must have done that the second semester. Anyway, somehow or another, I ended up in real analysis. I feel like this was my second semester. I could be remembering this wrong. Maybe it was my third semester. That would make more sense. Anyway, there was a semester. I was in real analysis. That same semester, I was taking electromagnetism. All right? And so in my real analysis class, I'm being raked over the coals for not saying C is a real number after I've already said it's a real number at the start of the proof, right? Like it's just crazy, the level of rigor. Just obnoxious, really. And then in my electromagnetism class, the professor asks us a question. He says, so let's let, what is, well, he said it like this, and there we use this notation. Theta of t was equal to 0 if t is less than 0, and 1 if t is greater than or equal to 1, right? So the graph of this thing looks like, I mean, it's the unit step function I was talking about a second ago, or you might call it the Heaviside function, right? All right? And so we're in that class, and he says to us, he says, what's the derivative of the step function? And I'm in real analysis, and I have been, besieged with rigor, and I'm like, derivative? What are you talking about? You can't differentiate this. It's discontinuous, right? At a minimum, you need continuity to calculate the derivative. Even that's not enough. But then the teacher basically mocks all of us for not knowing, obviously, that the derivative with respect to t of this is the Dirac delta function. Which, once you see it, you can't unsee it, right? Because that's exactly what it is, right? You're going from, you increase by 1 unit, poof, like that, instantly, And if you try integrating this, it works. Like, how can I say? How did I go?
I was just going to say out more.
What's that, Audric?
Oh, I see it. No, yeah, of course it's direct delta function. That's what we're talking about.
Yeah. So I mean, of course, if you
That's because you're evaluating at 0
Right, and if we replace this not with the step function, but with sort of a tamer version of things, right? And this is kind of the next thing the book is getting into, is, well, what if you did this, you know? And then the next one maybe is like that, you know?
Or like you're approaching an asymptote.
Yeah, like maybe this is, you know, F1, this is F2, and as, you know, Fn goes to theta as n goes to infinity, right? And you can look at the derivative, right? The derivative is like, it's 0, right? Except here where it's, you know, and then it's for my stupid family. But I mean, the derivative is kind of stupid too. It's. I mean, the graph looks like this for my stupid one.
Not to interrupt, but when are we meeting with the affiliate?
I told him 4:20 your time.
4:20 my time. Okay, it's 4 o'clock now, by the way.
Okay, so we got maybe 10 minutes. Are we already at 5? Oh, yowzers. So anyway, yes, indeed this is true, and the careful proof of it is given on page 294. He gives the distributional proof that the derivative of the Heaviside function is a direct delta function. And there it is. There's in detail the proof of it. So that's pretty neat. Because of course you can see it and believe it, right? But it's nice to see an actual proof. Let's see here. Next he defines weak distributional convergence. And if you look ahead to page 296, you know, he starts to build these ones, Audric. You know, these direct.
Yeah, I've got, yeah.
Oh, you got it. Okay, cool. He starts to build the direct delta function from, you know, the sequence of functions. And then he proves that the distributional derivative of a sequence of distributions is the derivative of the limit of the distribution. And then he does antiderivative. And then he has theorem 6.22, which says that if the distributional derivative is 0, then f is in fact a constant function. Then he again defines, now what he does next is he's defining all of this, instead of for Rn, for a subset of Rn. So like on page 298, he starts defining what is a test function on omega, and then convergence of test functions on omega. All of the theorems we had before, but now for test functions on an open subset omega. Notice that Leibniz formula there, Jacob. That's how to look at that. That is a bad formula. Page 299. He shows you how to take the arbitrary multiderivative of a product of a function and another and a distribution in terms of, you know, a product of combinatorial symbols and the appropriate derivatives of the function. This is the product rule, the higher product rule. This is the big product rule. At some point in your life, you should try to prove this. You know, like I don't think I proved this one. I proved it for like one dimension. Then that brings us to section 6.3, which is on Sobolev spaces, which is beautiful, and you'll hopefully take a course on that in grad school. And I think that's kind of it for me in chapter 6. I mean, I've got some tabs over here. I mean, he comes back and he revisits Green's functions from the perspective of distributions, and that's like pretty cool to read. Let me see if I can say something here. He's got a whole slew of differential equations he calculates the Green's functions for using all this distributional technology. He gives a proper definition of the fundamental solution that I touched on earlier today on page 306. That unit impulse idea, he circles back and does it for an arbitrary differential operator. Got a bunch of examples, Laplace's equation. He gives a careful definition of Green's function on page 307. Shows how you can use that to understand different equations of mathematical physics. And then he's got about a 2 or 3 page derivation on like 309, 310, 311. Here he's doing the Lagrange formulas that we saw in one dimension. I worked them out when I went through Haberman. I looked at these formulas in one dimension. Here's the analog of the Helmholtz theorem, but now done for differential equations over several variables. That's also in the book by Haberman that I mentioned, but Haberman? I think Haberman. But this is all like really, really beautiful stuff. But I think that's a pretty good place for us to stop. I think I've showed you what I need to show you for this course. Sorry I haven't showed you more. I think you'll learn a little bit more because I've assigned you a couple homework problems from this material. So like working through that homework problem will maybe make this stuff like gel a little bit more. There's a really cool example at the end that I was going to go through if I had time, but we don't, where he uses both the Fourier transform and the Laplace transform in concert to solve a differential equation. So like I think that's a wave equation solution. It's pretty cool. But anyway, next time we meet in this course, we'll be talking about quantum mechanics. So that's where we're going.